Welcome to this explainer. Okay, so if you work in a medical laboratory, you already know that quality control is, well, basically your daily bread and butter, right? But today, we're not just talking about checking off boxes to keep the analyzers happy. We're going to really look at how we control the actual risk of producing unreliable results that could seriously compromise patient care. Let's jump right in.
Picture this. It's a high-stakes, real-world scenario you might face on any given Tuesday. A critically abnormal glucose value just comes off the analyzer. But right beside it, you notice the daily quality control result is sitting completely outside acceptable limits. So, what do? Do you go ahead and release the patient result because you know the doctor is waiting? Or do you slam on the brakes and reject the entire run? Answering that exact question with total, absolute confidence is what this whole explainer is about. So, we're putting this topic under the microscope today. We'll quickly review why quality control really matters, break down the Levey-Jennings chart, understand the two main types of laboratory error, apply the famous Westgard rules, and then put you to the test with some accept or reject scenarios. Starting right off with Section 1, why quality control matters. Let's establish exactly why we're plotting all these points in the first place. The ISO 1589 standard actually makes our mission incredibly clear here. Our primary job isn't just instrument maintenance. No, it's actively controlling the risk of putting out a bad patient result. The World Health Organization defines this as continuously assessing laboratory work and emergent results. Ultimately, your quality control procedures are the only guarantee that the test results leaving your lab are actually fit for use in providing safe, effective patient care. So, how exactly do we track this reliability day in and day out? That brings us to Section 2, the Levey-Jennings chart. Before we even look at a chart, we really need to nail down two foundational statistical concepts that define our testing targets and, basically, our acceptable wiggle room. You know how it goes. When a lab sets up a control, they test it repeatedly, usually around 20 times or so, just to find the mean, which is the central target concentration for that control. But, as we all know, no machine is perfect. There's always going to be a tiny bit of acceptable variation, and we measure that expected variation using the standard deviation, or SD. Now, statistically speaking, what's really fascinating here is the normal distribution of the data. When your analytical process is behaving normally and it's perfectly in control, 95.5% of all valid quality control values are going to naturally fall right within plus or minus 2 standard deviations from that mean. That means only about 4.5% of perfectly fine data will occasionally just stray outside that 2SD line without there actually being anything mechanically wrong with the analyzer. And here is how we visually graph that exact concept, the famous Levey-Jennings chart. We draw the mean horizontally, right through the middle. Then we mark out our standard deviation limits above and below it, plus and minus 1, 2, and 3 SD. On that horizontal x-axis, we're tracking our successive days or runs. So every time you run a control, you plot a point. If the point lands within plus or minus 2 SD, well, just like we learned, the run is generally accepted as being in control. But what happens when those plotted points start misbehaving and bouncing outside those lines? Let's move to Section 3, Types of Laboratory Error. It's absolutely crucial that we learn to distinguish between random error and systematic error. Random error is, well, exactly what it sounds like, an unpredictable deviation. It usually affects test precision. A lot of the time, it's just an expected statistical fluke, something like a tiny bubble in a pipette. Systematic error, on the other hand, is a whole lot more dangerous. This is a consistent bias that directly affects accuracy. It's essentially a giant red flag that there's a fundamental system failure, like a degrading reagent or a calibration that's failing. So when you're examining your chart, you're actively hunting for specific visual cues that warn you you're losing test reliability. For systematic error, you're looking for two big things. First, a shift. This is an abrupt, sudden change where consecutive runs suddenly fall completely on one side of the mean. Or you're looking for a trend. This is a gradual change moving steadily in one direction, like a line just slowly, inevitably marching up or down the chart, day by day.
Now, to stop guessing and start making totally standardized decisions about all these points, we use a multi-rule system introduced by Dr. James Westgard back in 1981. Welcome to Section 4, Applying Westgard Rules. Dr. Westgard created a brilliant shorthand notation for this. Our first rule is the 1-2S rule.
The really crucial thing to remember here is that this one is merely a warning. It triggers when a single point falls outside the 2 SD limit. Why is it just a warning? Well, remember earlier, about 4.5% of perfectly valid results naturally land here anyway. So if you see this pattern, your action is to investigate. Look at previous runs, but whatever you do, do not immediately reject the run if there's no clear error.
Now the 1-3s rule, that is a hard stop. This pattern happens when one single control observation exceeds the plus or minus 3 SD limit. This indicates either a completely unacceptable random error or the dramatic beginning of a massive systematic error. When you see this, you must reject the run immediately and halt all patient results. No exceptions.
Okay, let's look at the 2-2s rule. This triggers when 2 consecutive control results fall greater than 2 SD on the exact same side of the mean. This one identifies pure systematic error. It's essentially warning you of a systemic bias affecting your testing curve. And your required action here? You guessed it, reject the run. Next up, we have 2 more rejection rules. First, the R_4S rule, which detects massive random error. This triggers when the range between 2 controls in the exact same run exceeds a massive 4 standard deviations. Say, one control is up at plus 2 SD, and the other drops all the way down to minus 2 SD. Then we have the 4_1S rule, which spots systematic error. This happens when 4 consecutive points slowly drift and just stay past the 1 SD line on the same side of the mean. Both of these rules mean you absolutely have to reject the run. Finally, there's the 10x rule. For this one, you'll see a pattern of 10 consecutive results just lingering on the exact same side of the mean, even if they aren't crossing major SD lines. This proves a systemic bias across a broader concentration. Maybe your calibration has just slowly drifted over the last week and a half. Therefore, you've got to reject the run and recalibrate.
Okay, let's actually put this into practice and test those decision-making skills. Moving into Section 5, accept or reject. I'm going to give you a few scenarios, and you have to decide.
All right, scenario 1. You run a control, and the result is at plus 2.5 SD. But all your previous runs were tightly clustered near the mean. So accept or reject. Well, think about what rule is being triggered here. Since this is an isolated 1S2 warning, and there's absolutely no systematic relationship to those tightly clustered previous runs, it's acceptable random error. You can go ahead and accept the run, and those patient results can be safely reported. Now for scenario 2. You test 2 different control levels in the same run. Level 1 is at minus 2.2 SD, and level 2 is at minus 2.4 SD. Accept or reject. Look really closely at the pattern. We have 2 consecutive QC results in the same run, and both are greater than 2 SD on the negative side of the mean. That is a glaring violation of the 2-2S rule across your controls. It indicates a systematic error affecting your whole analytical curve, so you must reject the run. Absolutely no patient results can go out. Summarizing this entire framework, we really just need to ask 3 basic questions every time we look at our charts. What pattern am I seeing? What type of error does it actually signify? And what action is required? Notice here how literally every single rule, except for that initial 1-2S warning, requires an immediate rejection of the run.
Before we wrap up, we've got to address some bad habits. You need to be incredibly careful to avoid these common pitfalls in the lab. Honestly, one of the most dangerous things you can do is just repeat a failed QC over and over again until it randomly falls into range without ever investigating or fixing the root cause. If you violate a Westgard rejection rule, you cannot just test a new vial of control and pretend that first failure didn't happen. Which brings us right back to our hook from the very beginning of this explainer, that critically abnormal glucose value sitting right next to a failed QC. Here is your definitive, absolute answer. The results of patient testing should never be released if the QC results do not meet your target values. You've got to correct the problem, whether that means recalibrating or fixing the reagent, rerun those controls, and then, only when the system is actually back in control, can you rerun the patient sample. Ultimately, those tiny little dots on your Levey-Jennings graph, they represent real medical decisions and real human lives. Quality control is definitely not just some regulatory nuisance you have to deal with. It is literally the absolute front line of patient safety. So I'm going to leave you with a critical question for your next shift. The next time you plot a point on that chart, are you going to look at it just as a random data point or as a promise of reliability to the patient waiting for their results? Keep learning, stay precise, and thanks so much for joining me on this explainer.